Eleanor here. We're going to talk about friction today. So we have mentioned in class already that friction is an opposing force, and we've talked a little bit about how there are lots of different kinds, and it's pretty important. So we're going to take a deep dive into that today and talk through our notes. So friction technically does oppose motion. When we draw it, we always draw it opposite of the direction of motion. But think about it. Think about whether you'd be able to move at all if you didn't have any friction, right? Imagine like walking on ice, or if you've ever hydroplaned in your car, when your wheels spin and you don't have any control over that, right? That would be a lack of friction. Okay, so friction is actually hugely important. We rely on that. When you set your foot down, you assume that you can push off to step forward, right? And that assumption is based on the fact that there would be friction between your shoe and the floor. If there wasn't, then you would just slide and you wouldn't be able to go anywhere. Okay, so friction is super important. In class, we're going to watch the Magic School Bus, at one of the old ones where they play baseball without the use of friction, and it's a great example of what would happen if we didn't have friction. So you can look that up probably on Netflix or YouTube or something if you want to see it. But the big idea is just that although friction opposes motion, it's also extremely important for motion to occur. Sliding friction is the friction that we're going to focus on. There is fluid friction and there's air resistance as well. But sliding friction is where we'll kind of camp out for the most part for our class. And so what that comes from is just that surfaces are very rough microscopically. Okay, you've got a picture here of two surfaces rubbing against each other microscopically. Those surfaces are very, very rough, and so they catch on each other, so to speak, and that gives you the friction. We know that friction creates heat, right? When you're cold and you do this, you're using friction to warm up your hands. When we get into energy in about a month or so, we'll come back to that idea that friction and heat are intertwined. And that leads us to our equation. So we actually can calculate sliding friction, okay? In our picture, we've got a guy here who's pushing this box, and we'll extend his little sword there so that he's actually touching it so we can have an applied force. So he's pushing to the right. Friction is opposing that motion to the left. We've got normal force from the surface, and we have, of course, the weight of the box. Our formula for friction is this one here that says that the force of friction, which would be in newtons, is calculated by multiplying the coefficient of sliding friction, which is that, times the normal force, which is also in newtons. The coefficient is actually a ratio. People have measured and determined the coefficient of friction for lots of different surfaces. It's basically a comparison of roughness of surface. Okay, so since it's a ratio, it doesn't have a unit. All right, so this is one of our very rare numbers where it's just the number with no unit. Secondly, it's typically extremely small, usually less than 1. And the smaller it is, the smoother it is. So ice skates on ice, this one is super, super smooth, right? Almost no friction at all. So that coefficient is extremely low. Sandpaper on wood is a lot of roughness, right, between the sandpaper and the wood, and so the coefficient is relatively high. When you calculate, if you get a number like 12, then that's too high and something is going to wry in your calculation. All right? Okay, so we know about the coefficient. The second part of the equation is the normal force. So the normal force comes from the surface, right? And the surface is what's generating the friction or causing the friction. So it's important. We also know that for anything on a flat surface, normal force is equal to the weight on the object. Those two are perfectly balanced, like in our picture here. So that means that the heavier the object, the greater the normal force, and also the greater the frictional force. And you know this if you've ever tried to move something really heavy across a rough surface like carpet. The heavier it is, the harder it is to move it, right? Because there's just a lot of friction. Okay? All right, so that brings us to our example. So in our example, we have a 5 kilogram box sitting on the floor. A student is going to push on it with 20 newtons of force. The coefficient of friction between the box and the floor is 0.3, and we want to know, does the box move? All right, I'm going to move my face so that you can fully see this problem. So step one, like all of our normal problems, is we're going to start with a free body diagram. I like to put the mass inside of the object just so I don't have to search for it later, but you can represent the object as a dot if you like. Okay, we know that this box has a weight on it. We assume it's not falling through the floor, so it has a normal force as well. They tell us that a student is pushing with an applied force of 20 newtons, and then we can assume that there's some friction here because they gave us a coefficient of friction, and it's a friction problem. All right, we want to kind of highlight the 0.3 and remember that that's our coefficient. That little letter, by the way, I forgot to mention earlier, is a Greek letter. It's a lowercase mu, and so that's not a typo, that's just a little Greek symbol for this. Okay, so for figuring out if the box moves, we need to know what's happening to the net force, right? Is the friction equal to 20 newtons, equal to the applied, or not? So we're going to start by finding the weight because that's easy to do with our Fg equals mg formula. And so the weight is going to be 5 kilograms times 9.8 meters per second squared. And that gives us a weight of 49 newtons. Okay, we know that Fg equals Fn, right? The normal and the weight have to be the same if our box is sitting on the floor and not falling through or rising up. Okay, now that we know the normal force, we can use our force of friction formula that said force of friction equals the coefficient times the normal force to solve for the force of friction. So they told us the coefficient was 0.3 in the problem, and then we just found that the normal force was 49 newtons. And so we're going to multiply those two, and that gives us a frictional force of 14.7 newtons. Okay, so I'm going to add that to my little picture so that I've got a visual. Okay, so does the box move? Well, look at our force of friction and our applied force. They're not equal to each other. So the answer is yes, the box moves. And the way that we know that is that FA and FF are not equal to each other. In fact, it's accelerating because they're not equal to each other. Okay, so knowing that actually allows us to solve for our acceleration. We can do that first by solving for the net force and using our sum of all forces equation. The reason we're going to use that one first is that eventually we want to use the second law formula, but we don't know the net force. Okay, so we're going to write our own equation. We're going to say F net equals FA minus FF. Remember that F net equals sum of forces always means write your own equation based on the picture that you have. So F net will equal 20 newtons minus 14.7 newtons, and that gives us a net force of positive 5.3 newtons. So 5.3 newtons to the right. Okay, so now we can use our second law formula that says F net equals ma to solve for acceleration. So positive 5.3 goes in for F net. Mass was 5 kilograms. I'm looking for A, so I'm going to divide by that mass to get A by itself, and I get an acceleration of a positive 1.06 meters per second squared. I try to think about this logically. Does it make sense? And yes, it does. The box has a net force to the right. The applied force is greater, therefore the acceleration should also be to the right. And that's all there is to sliding friction.